When we first studied linear systems, we talked about the response, the output of a linear system, was the sum of two signals. One was the zero input response, and the other was the zero state response. The zero input response is the output of the system due to the initial conditions acting alone. That is, there is no input in this case. The zero state response is the output due to the input alone. In this case, all initial conditions are zero. We call the output, due to both initial conditions and the input, the total response. And for linear systems, the total response is the zero input response plus the zero state response. We simply need to add the two signals together. To indicate to you how important this result is, I am showing it here inside the magic golden frame. The total response is the sum of two signals, the zero input response and the zero state response. This is true for linear systems and only for linear systems. To give you a better understanding of this concept of total response, I'm going to consider a system which is a baseball. So the motion of the baseball depends upon two things. It depends upon the initial condition, that is the position and velocity of the ball when it's leaving the pitcher's hand. And it also depends upon an input coming from the batter. This input is the force of the bat upon the ball. So we have an initial condition and we also have an input that determines the ball's motion. We can represent the dependence of the output on the initial conditions and the input in the following diagram. The total response of the system is dictated by both the initial conditions and by the input. This will be true for all systems, whether they're linear or not. The special thing for linear systems is the nature of this dependence of total response on the initial conditions and the input. Let's examine that a bit more closely. First, let's consider the response of the system to the initial conditions alone. So this would be the motion of the ball in response to the initial velocity and position of the ball given by the pitcher. The ball would continue to move in whatever fashion it was pitched in. There would be no input from the batter. Now let's consider the response of the ball to the input alone. This would mean the ball would have no initial velocity or position. It would be as if the ball was sitting on a tee. Then the batter would apply the force with the bat, and you'd have the response to that hit. If the baseball system was linear, then we could find the motion of the ball in response to both the initial conditions established by the pitcher and the force input by the batter by simply adding together those two motions. That is, the motion of the ball as established by the pitcher via the initial conditions, and the motion of the ball as dictated by the batter through the input. We could take those two motions and add them together as signals to form the total response, the response of the ball to both the initial conditions and the batter's hit. If the baseball system is not linear, then this cannot be done. The response of the system to the initial conditions established by the pitcher and the force input by the batter, the response to that won't be the simple sum of the response to the pitcher's initial condition and the response to the batter's input. If the system is nonlinear, the total response is still due to both of the causes, the initial condition and the input. But the total response cannot be found simply by adding together the two motions. For the nonlinear system, this superposition does not hold. So now let me remind you of the terms that we use for these two responses. The response of the system due to the initial conditions alone is the zero input response, and the response of the system to the input alone is the zero state response. Over the next several lectures, we're going to spend a considerable amount of time talking about how to find the zero input response for a linear system and the zero state response. Once we have these two, of course, we can add them together to find out the total response for the linear system. Let's now define the types of linear systems that we'll be considering throughout the majority of this class. In this presentation, we're going to talk about a subclass of systems, which are very important. In fact, this is the class we'll spend most of the time in this course studying. This is the linear time invariant continuous time systems, abbreviated LTIC. In this presentation, we're going to be concerned with actually a subclass of all LTIC systems, the ones described by ordinary differential equations. As you recall, we saw linear systems before, which were not described by differential equations. A good example would be the moving average system. The moving average system is a linear time invariant continuous time system. We already discussed linearity, and time invariance can be easily shown. What about continuous time? Continuous time refers to the fact that the independent variable time is a continuous variable and may take on all values on the real number line. This is opposed to a discrete time system, where time occurs in increments, that is, 1 second, 2 seconds, 3 seconds, and the times in between are not represented along the independent variable axis. All physical systems are continuous time systems. Some algorithms, however, are discrete time systems. In this course, we will almost exclusively examine continuous time systems. So let's now focus on this particular kind of continuous time system described by ordinary differential equations. Our model is shown here. We've seen this before. It's a differential equation in terms of the input signal x and the output signal y. We see n time derivatives of the output signal y and m time derivatives of the input signal x. The coefficients which are multiplying the output signal and its derivatives and the input signal and its derivatives are given by the a's and b's. These coefficients are constant, so the system is time invariant. If the coefficients were functions of time, the system would be time varying, although it'd still be linear. This differential equation is rather unwieldy, so we're going to introduce a new notation in order to make it easier to write. Everywhere there is a ddt, I'll just change that symbol to capital D. That's the differential operator. And then I can write my differential equation like this. We have a polynomial in the differential operator, q of d, which is multiplying y of t. And we have a polynomial in the differential operator, p of d, which is multiplying the input signal x of t. You notice the coefficients of our differential equation appear as coefficients of these polynomials. So we can write our differential equation in a very compact form. Q of d times y of t equals p of d times x of t. The order of the polynomial q is given by n. The order of the polynomial p is given by m. And I'll note that m will be less than or equal to n in almost all physical cases. Now, to proceed, we'll assume that m equals n, but the case of m less than n can easily be recovered simply by setting some of the coefficients of the polynomial p of d equal to 0. So treating the case of m equals n is completely general, and we'll proceed in this fashion. In our next lecture, we'll examine how to find the zero input response of a linear system in this form. Recall that the zero input response is the response of the system to initial conditions alone.